present discussion will be about something I call Thomas Kuhn's paradigm of science. That may seem a rather strange locution, but I hope by the end you'll realize that it's necessary to think of his paradigm of science as itself a paradigm, precisely because he's transcended what we might call correspondence theories of science on behalf of something I would call coherence theories. Kuhn wrote for something called the Encyclopedia of Unified Science, which was really to be the great final product of the logical positivists' philosophy, a landmark study called The Structure of Scientific Revolutions. I've always found that ironic because it is one of the critical texts which completely undermined the logical positivist movement and tradition. A philosopher at Columbia University, Arthur Danto, once told me, I did the work with him, The Structure, and he once said to me that he thought this was the most influential text of the 20th century. And since then in my research, my own reading has suggested that he's right. Literally almost every text from anthropology all the way over to art criticism will have somewhere in there a footnote to Thomas Kuhn, or the word paradigm will show up somewhere. So I would argue that in many ways it may well be the most influential high cultural text of this century. Kuhn himself was a doctoral candidate in theoretical physics at MIT with a strong avocation for philosophy of science, and also had a reasonable propensity for the history of science. And somewhere on the way to finishing up his dissertation, he came across an anomaly which veered him in his career path. His exposure to the history of science led him to conclude that the positivist theory of science could not adequately account for the actual historical development of the natural sciences. And he became concerned, almost obsessed, with trying to find a better model, or as we'll argue, paradigm, for how science actually works. So what he does is he argues against the received conception of science as commonly held, a sort of steady and incremental accumulation of observations, data, discoveries, and inventions. That there's this sort of cumulative, steady, and sure process going on. And Kuhn found that that was not in fact the case at all. In response to, for example, the logical positivist's view that science is really defined by its methodological rules, right, by its semantic conventions for building theory, Kuhn points out that such directives are, in and of themselves, insufficient to generate unique conclusions to any kind or most kinds of interesting scientific questions. That without more background theory than just those rules, there's no way that two different observers will agree on what the significant phenomena are. So what Kuhn argues is that the history of science is actually characterized by periods of peaceful and what he calls normal research, which are punctuated by epochs of crisis and transformation, which he calls scientific revolutions. And I would urge that what Kuhn is doing in a way is pulling the theory of science away from its sort of logical moorings, away from a sort of conception of science by means of rational reconstruction, and instead is historicizing it. In fact, offering a historical sociology of scientific communities and problems. Right? So Kuhn is arguing that an empirical study of science would in fact take the form of a historical sociology of scientific communities and disciplines. What distinguishes mature from immature science for Kuhn is the large degree of consensus held by practitioners at any given field. And that's the most signal sociological factor distinguishing a mature from an immature science, is that the practitioners of a mature science all agree on certain basic fundamentals. In fact, the early, immature development of most sciences is characterized by a continual competition between distinct views of nature, each of which is completely consistent with the given rules and dictates of scientific method and all the possible observations. So he says, before you get to modern, mature science, you actually do have science before that, but you have people arguing at cross purposes, and there's no way of proving which is right or wrong. And I think we saw a wonderful example of that in the Ionian philosophers, the pre-Socratics, each of which followed scientific method, each of which had observations, each of which completely contradicted the ones before them, none of which were decidable one in favor of the other. Effective research, right, modern science, or what Kuhn calls normal science, can't begin until a community of scientists, practitioners, people working in the same discipline or field, agree about the basic entities that they're talking about. They have to also agree how these entities interact with each other, and more importantly, how they interact with our senses, so that we can model what would count as an observation. And finally, they must agree as to what counts as a legitimate question, and what would demarcate the range of legitimate answers and solutions to those sorts of questions. And this agreement is reached by means of one or many paradigms, a very important word in this exposition. In the absence of such paradigms, all facts seem equally relevant to any given issue. And such fact-gathering, as we would find expressed by, say, Francis Bacon, is completely indiscriminate because we don't know what to look for or how to describe it. All right, a paradigm for Kuhn is defined as a universally recognized scientific achievement that for a time provides model problems and solutions to a community of practitioners. Such achievements must be unprecedented enough to gain adherence. And yet, they must also be open-ended enough so as to allow such adherence to solve problems which had been postulated without being completely resolved. Right? So there's a sort of symbiotic relationship. You must make a breakthrough, but leave it unfinished enough so that if I acknowledge the breakthrough, there's something for me to do, which is to fill in the details. In any discipline, a paradigm will present standard cases or illustrations of the various theories and their conceptual, observational, and instrumental applications. These cases are exemplars, or paradigm cases, and when situated in their theoretical context, when embedded in the various, in mathematical sciences, formulas, they constitute the paradigms proper. I want to flesh this out with a couple examples of distinct paradigms in a field that most of us are pretty well associated with, that of dynamics, the study of motion, objects in motion. First example I'll draw we'll call Aristotle's paradigm. I draw these examples from Stephen Toulmin's remarkable little book, Forecast and Understanding. Aristotle said if you want to think about the problem of motion, dynamics, consider the following paradigm case. You've got a cart or a sled resting at level ground, and it's got to move. So you either push it or you put a horse in front of it. Right? So what you're looking for are the force being added by the horse and the resistance of either the rockiness of the ground or the friction of the wheels. And his basic finding was, if you run that experiment, you will find that objects tend to stay at rest and will move only as long as a force is applied to them. And what you would then come up with as formulas, although Aristotle didn't, would be something to the effect of what sorts of weights of sleds or carts move at what rate given a certain number of horses. And in fact, that is a very useful sort of understanding. We in fact have the notion of horsepower, obviously, which draws on just that sort of a conceptualization. So that was the first, let us say, sophisticated system of dynamics. One paradigm. Let us then turn to the Galilean paradigm. Galileo thought that Aristotle was quite wrong. What he wanted to do was explain what Copernicus had posited, right? That, in fact, the Earth is in motion around the sun, and that all of the planets, rather than going in epicycles, have simple circular motion, orbital motion. So Galileo posited the following paradigm. He said, imagine a ship at sea. If you apply a force to that ship, wind in the sails, and there's no frictional force in the water, we should expect that ship not to stop as soon as the wind stops blowing, as Aristotle suggested, because the force is removed, but rather to continue moving, as it were, right all the way around the world. Once the force is applied, that force gives it an inertia, a momentum, which keeps it flowing right around the world. He didn't feel he had to explain why it would go all the way around the world, because orbital motions were for him paradigmatic or natural. It's natural for things to circle the world once they're given a certain amount of force. The only thing that stops a ship from doing that are frictional forces in the water, and therefore it needs more and more wind to keep moving. Now I want to turn to one last paradigm to illustrate this, and that is the Newtonian dynamics. Newton takes the exact same case as Galileo and says, imagine that ship. You blow wind on it, there's no forces on it except for that wind. It won't go around the Earth at all. Motion, natural motion, is rectilinear. It'll go right off on a tangent to the Earth and flow into outer space. And then he says, and I can explain the orbital motion of the planets, not because it's natural for them to orbit, but because there are gravitational forces which counteract the tangential motion that is natural, rectilinear motion. And therefore, you put those two factors together and draw a vector, and you get a big circle. All right? So that's three distinct paradigms of the same problem. And note, they all have different cases. There's the cart, there's the ship flowing around the Earth, and then there's the notion of removing gravity and seeing the ship fly straight out on a tangent from the Earth. Kuhn argues that such paradigms are prior to the rationally reconstructed, quote, rules of science. In fact, the rules of science are created by some philosopher comparing the various paradigms and current research topics in any scientific community and abstracting from them what they seem to have in common. If you change the historical venue, you'll get different rules of science, different methods. And so his point is, always what practitioners follow are the paradigms, never the rules. It's only a positivist who would be concerned about the rules. In fact, rules or methodological issues only become significant in the history of science when you come across periods of paradigm crisis, right? When your paradigms no longer work, your accounts no longer will colligate the observations that they predict, then all of a sudden scientists start saying, well, we've got to think about the method here. We've got to think about, well, what do we mean by these sorts of terms and stuff like that. So for the most part, as long as a paradigm is working effectively, no one will even bother mentioning scientific rules or methods. It's just not significant. The paradigm constitutes its own rules. So this priority of paradigms to pure theories and rules is exemplified in the actual pedagogy of scientific instruction. Look at a science textbook. It will always give you particular cases. And those of you who have taken science, and all of you have at some point, even at the high school level, you'll remember that the first thing in the beginning of your science textbook were not a list of rules, right? But rather particular formulas and then say, try this experiment. And in fact, when you take a course in science, it's the same thing. Such theories are always embedded in paradigm cases, always embedded in particular lab experiments, which give you a working theory, a handle on how to apply the paradigm or model to the world. And there's a good reason for this. The study of paradigms prepares one for membership in a scientific community, since shared paradigms result in shared rules and shared standards of practice. Paradigms also have another important effect. By demarcating things around certain exemplary cases, you actually limit the range of acceptable questions and relevant facts. And this is important because there is no paradigm that can face all of the facts it can be confronted with. Literally none. Paradigms are thus, in a sense, underdetermined by the facts. They are constructions or models or interpretations of phenomena which are foisted onto the world to make some sort of order into it. And Kuhn's paradigm of the paradigm is the famous visual gestalt, of which I've given each of you an example. If you'll look at the visual gestalt, you'll notice that you have three circles at the center of which is a point which is intersected by three lines. What makes it a gestalt is, it is completely tenable to interpret that point as being the back of, say, a floor with two walls coming off it. Can you all see it that way? You could also see that point as pointing towards you. Right? This is the front side of a cube. Either way is a legitimate interpretation of the lines. The lines underdetermine the interpretation. There's more than one way to read it. And Kuhn argues that paradigms are very much the same way as the visual gestalt. That nature has an interpretation imposed on it by a particular paradigm. And that you may well find that there are more than one way of interpreting those phenomena, more than one tenable paradigm. Okay, that allows us to get into the discussion of something we'll call normal science. Normal science, or normal research, is paradigm-based, which is to say it draws upon previously laid out and accepted paradigms. Kuhn describes such normal science as a sort of mopping up, or tightening the fit between the facts displayed by the paradigm and the paradigm's predictions. Right? The paradigm gives us a model of the way the world should work, and then normal research tightens that fit between the world and the paradigm. Now, such normal scientific research may in fact require a further articulation of the paradigm itself. Right? Take, for example, Newton's notion of two important things, that rectilinear propagation of motion and the notion that all entities are corpuscular. That led to the need to develop a new optics, a new theory of light, that light was in fact rectilinear, right? That it always traveled in straight lines. So what we have then is, by focusing on such a narrow range of topics, straight line things, particles moving in straight lines, photons in straight lines, paradigms allow normal scientists to study some very small part of nature in incredible depth and detail. So that we'll have a remarkable amount of rich complexity in a single particular small part of nature. The problems of normal scientific research and experimentation, according to Kuhn, fall under three heads or categories. The first would be the investigations of facts that the paradigm says are exemplary or particularly revealing about the paradigm. For Newton, in his discussion of dynamics, these were experiments dealing with pendulums. Right? He had not yet had the ability to analyze parabolic motion, the shooting off of cannonballs and stuff like that. That was subsequent normal science mopping up. Initially, you looked at the paradigm cases, pendulums swinging back and forth. You might also, another head or category of normal scientific research is investigation of esoteric facts that can be compared to the paradigm's predictions. An example would be Newton in astronomical observation. Right? Given Newton's laws of gravitation, people were able to posit, given their observations, that somehow or other there must be another planet out there, distorting some of the orbits of the planets we can observe that are fairly far away from us. And therefore, it was necessary to develop new telescopic innovations, technologies, to be able to actually observe Neptune or Pluto or whatever planet it was. So that's another sort of experiment, looking into rather esoteric, difficult facts, which can be compared to the paradigm's predictions. And then the final category is research done to extend or articulate the paradigm, to resolve its ambiguities, or perhaps even to solve problems which had hitherto only drawn attention. Now, in the mathematicized sciences, this can be, and is very often, the search for what are called constant values. Right? There's a gravitational constant, which a lot of 19th century scientists, spent working on figuring out exactly what was the precise number of that constant. Those who know some chemistry know of Avogadro's number, calculating exactly what is Avogadro's number. Another form of such research into extending or articulating the paradigm is the construction of quantitative laws within a particular paradigm. So given the paradigms of electromagnetic phenomena in the 19th century, Maxwell's laws, for example, might be such an articulation. You build quantitative laws which can be fit into the paradigm and therefore extend it. And then, of course, there are experiments which one might use to decide how to apply the paradigm to a new area of interest. And I already suggested one such topic, that of optics, the attempt to extend Newton's notion of the rectilinear propagation, movement of bodies into the rectilinear propagation of corpuscular light, light made up of photon particles. Well, normal science, then, can be thought of as a sort of puzzle solving, right? Very much like solving a jigsaw puzzle. Note something. A jigsaw puzzle is designed to be solved. Just like the problems of a paradigm, they are designed to be solved through normal research. A paradigm offers problems that are presumably solvable, and other problems that are not solvable in the paradigm are simply dismissed as metaphysical or irrelevant, or well, that's another field. That's chemistry, not physics. Note a common similarity. Both paradigms and puzzles have rules or conventions of construction. This may not seem obvious at first, but there is actually a rule for building jigsaw puzzles, isn't there? You cannot take any two given shapes, take out a scissor, and cut them till they fit. There is a rule. They must actually interlock, and tightly so. If you can interlock them and there's a large space between a piece and what it goes into, it's not considered a legitimate construction. Well, so is the case with paradigms. Right? They give you rules for solving the problems posited by the paradigm. So pre-paradigmatic or non-normal science can be likened to randomly mixing the pieces of two distinct jigsaw puzzles. It doesn't make a pattern. It doesn't fit. So, and pre-paradigmatic science is just like that. There are as many different ways of constructing that ill-fitting puzzle as there are different people with propensities to do so. And each of them is equally legitimate, given the rules of puzzle solving, and equally arbitrary. Right? Hence the significance of paradigms for delimiting the range of possible problems and focusing attention. Now this turns to the question of anomalies, because anomalies turn out to be that which undermines paradigms. An anomaly is a fact or phenomena which violates the expectations or predictions of a paradigm. Right? X-radiation was discovered in just this way. Someone was doing an experiment, I think with various light experiment, and found readings which just didn't make any sense. Locked himself in the lab for 2 weeks, studied the phenomena, and eventually discovered, gee, there was something going on here that no one had thought of before, and had to articulate a new paradigm for it, or a new way of accounting for it. And anomalies are generated all the time, but the persistence and proliferation of anomalies generate scientific crises. If enough anomalies keep coming out in observations, you begin to lose faith in the paradigm. An excellent example here might be the Michelson-Morley experiments in the 19th century. Prior to the 20th century, scientists had agreed that there was an extremely fine substance which suffused the universe, which was called ether, and through which all the objects moved through. And you could gauge motion, in an absolute sense, in context of the ether. Well, Michelson and Morley did certain observations about the Earth's movement around the sun, and on the basis of the ether posit, they should have found certain results, which they didn't. The results came out such that it was almost as if there was no ether, as if there was nothing but a vacuum in space. And that created an anomaly, a certain amount of uncertainty, of anxiety in the scientific discipline at hand, which was eventually only solved, as we know, by Einstein's relativity theory. So what happens with these crises are, they actually blur the paradigm. They make it seem fuzzier. The rules get loosened, right? The structures of interpretation break down. And so normal science begins to become, quote, abnormal, begins to become problematic. Now, such scientific crises can be resolved in one of three ways. Normal scientific research solves the problem of anomalies after all, and the crisis abates. An example would be, again, think of the principle of the rectilinear propagation of light. There's a big anomaly. It doesn't seem to be a straight line when you stick a stick into water, or a pencil into a cup of water. Or when you look through a prism, light doesn't seem to be rectilinear then. And that was a crisis for the paradigm. And it was solved through normal science, through the positing of something called Snell's law, which argued that the rectilinear light waves, as it were, or light particles, are refracted through distinct mediums. And then subsequent normal science tried to come up with constants for various different mediums as to how the light would be refracted. Okay, so that's one way that a scientific crisis can be resolved. The crisis can just abate. You can solve the problem of the anomalies with the paradigm. There's another possibility, one that happens quite often in the practice of science. You try to solve it for a while, you work on it, and you work on it, and you don't get anywhere. And what you do is you simply shelve the problem. Say, well, it's a metaphysical problem, or, well, we can't solve it now, or let's not talk about it now, let's put it in another field. It's simply put on the shelf, at least for the time being, until a subsequent revolution occurs which can solve it. Finally, and most importantly, a new paradigm can emerge from the loosening of the rules which replace or supplant the old paradigm after a long period of crisis and struggle. Right? That is what we would call paradigm shift. Thus, a new theory will emerge which, when wedded to its exemplary cases, right, to its paradigm cases, will constitute the new paradigm. And that's exactly what we find with the transition from Newtonian physics or dynamics to Einsteinian. Long-standing theoretical crises give rise to new paradigms, even if the factual basis of such paradigms are problematic for the moment. And a classic example of this that Kuhn cites is the transition from Ptolemaic astronomy to Copernican astronomy. Ptolemy, you may remember, thought the Earth was the center of the universe and the sun moved around it. Now, it turned out each of them had equally accurate observations, and both of them could explain facts that the other couldn't. The observation of astronomical entities was not sufficient at the time to actually establish Copernicus's paradigm. But people had been working with Ptolemy so long and had led to so many problems that they said, let's just give this other guy a chance. And fortunately, Galileo actually was able to subsume some of those problems and solve them, and we got better observations from Brahe and Kepler. So my point, the point Kuhn is making, and I would urge it strongly, is it's not simply that the facts will always support the shift to a new paradigm. Simply a community scratching its head for several hundred years with Ptolemy and getting nowhere is enough basis to say, let's try the new paradigm at least for a while and see if it works. And it turned out to be fruitful. If it wasn't fruitful, they'd have gone back to Ptolemy. The point here is that no paradigm is ever destroyed by its anomalies. The anomalies create crises, but they do not destroy paradigms. The point is you cannot go back to pre-paradigmatic science. A bad paradigm is better than no paradigm. And the point here is, in the actual practice of science, if you have anomalies, and you're getting more and more anomalies, and you don't have a new paradigm, you'll just suppress them. It's better than going back to the state of random confusion that preceded it. An old paradigm can, however, be replaced by a new one, right? So when we had the Michelson-Morley experiments, we didn't throw Newton out the window. We kept Newton until Einstein came along. And then when we had a new paradigm that could account for everything Newton talked about, and then some other phenomena, subatomic phenomena, which couldn't be explained by Newton and the Michelson-Morley experiment, then we embraced the new paradigm. So we never lose a paradigm, we simply move to a new one. That process of paradigm shift, Kuhn calls scientific revolution. Such scientific revolutions are the key to scientific progress. So while normal science is infinitely fruitful, there is an inherent value to this sort of revolutionary activity that occurs when old paradigms break up and new ones replace them. That is the means of large-scale scientific progress. Without it, we would be stuck in probably a medieval conception. Okay, I think you've got a decent sense of what a paradigm is and how it relates to normal science. Kuhn argues, rather controversially, that theories derived from rival paradigms are what he calls incommensurable. That is to say, the meanings of the theoretical expressions you'll find in a paradigm are paradigm relative, which, again, they derive their significance from the system and law of concepts and laws and experiments in which they are embedded. The point is, Contra the logical positivists, there is no objective basis for choosing between paradigms. You do not have a set of rules where you can look at two paradigms and say, well, this one's more precise, throw this one out. That's not the way such decisions are done at all. There's no objective basis for negotiating the claims of distinct paradigms. If you have to choose between such theories or such rivals, it will instead be done on the basis of what I would call living it to the limit. Instead, what you do is perhaps half of you accept one paradigm, the other half accept the other, and then you each start your normal research. Whichever one of you, after 15 years, produces more normal research, that's the side we turn to. That's the way distinct interpretations of quantum physics usually are negotiated. That's the way, for some time before they remove the problem or solved it with another paradigm, problems of whether light was a particle, photon, or a wave was decided, which were more fruitful experiments. And that is the way almost all rival paradigms are negotiated, not through a logical process, but simply through experimentation. You try one, I'll try the other, we'll do our research, we'll publish our papers, and we'll see which turns out to be more fruitful in the long run. This highlights the pedagogical and practical need for textbooks. Right? Why science is taught the way it does. Lab experiments. We need a working theory rather than the sorts of rules and definitions that positivists offer. Okay, I want to suggest two things now. One, some of the larger implications of Kuhn's theory, and secondly, an anomaly for Kuhn's theory. The larger implications for Kuhn's theory is it devalorizes science in a certain way. It suggests that what is unique to science is the fact, the observable sociological fact of consensus on issues and problems. This is important because the positivists tried to argue that history and the social sciences were unformed, unfinished, that they ought to be fully scientific. And what Kuhn argues is, no, what you really mean when you say that is you think all social scientists should agree on a given set of problems, topics, and issues, and ways of solving them. But maybe that's not what we want in our understanding of human problems. Right? Maybe such consensus is besides the point when talking about issues of justice or political management or the running of the economy or something like that. Perhaps it's precisely there that you want diversity, distinction, a lot of different viewpoints. And he says there's in fact a sociological observation you can see on the basis of this. Pre-paradigmatic discourses almost always come in books. Paradigmatic discourses almost always come in articles. Right? Because since you have the paradigm worked out, you're working on a tiny, tiny feature of it. We may not want puzzle solving in literary criticism. We may rather want a large degree of free play, of looseness. Therefore, the claim that the social sciences and humanities ought to be scientized is in fact a confused claim. It is only the claim that we want to close off different venues. It is useful to close off different venues in nature. It gives us incredible detail and control. But that may not be what we want in our study of society and of humanity. I now want to turn to an anomaly that I find in Kuhn's. I don't think it's a crushing anomaly, and I think it's something he himself has acknowledged. It turns to the paradigm of the paradigm, the Gestalt. Gestalt has a particularly interesting set of properties. It's both transitive and symmetrical, which is to say, if we take a look at our cube, you can see that point in the middle as the back or as the front. And you can go back and forth, can't you? For some reason, however, scientific paradigms don't seem to work that way. For the most part, they're unidirectional. We haven't gone back to a Ptolemaic interpretation of astronomy. We haven't gone back to a Newtonian conception of space. We believe there's curved space now, right? It's not Euclidean at all. We haven't made that backward shift. And in fact, I've been thinking long and hard for a single example of such a reverse shift. I must say I found one, very esoteric and bizarre, Werner Heisenberg's reading of the Copenhagen interpretation of quantum theory, which he says argues that the electron is not anywhere. It's a potentia. So Aristotle was really right metaphysically all along. Such a case, however, I don't think will solve the problem of the anomaly. But now, to defend Kuhn's, I would say the following. How can we resolve the problem of this anomaly? I think Kuhn's is right. There's only three ways. Either I've missed something in my reading of Kuhn, or some other researcher will come across and say, you know, that's not really a big problem. Kuhn's paradigm can solve it. Or, the third route, it will create a crisis in the historical community, and the historians of science, and they'll say, well, they'll loosen the rules and create a new paradigm, which accounts for the intransitivity of paradigm shifts. Or if they can't, what is most rational, and here I agree with Kuhn's again, is they'll simply say, well, that's an interesting anomaly, but there's nothing we can do with it. If you don't have a better paradigm than Kuhn's, we'll stick with Kuhn's. And I think that, in a sense, exemplifies what I would urge as the coherence aspect of Kuhn's work, right? Here's, I think, the deep payoff. There is no way of comparing the paradigm to nature. You apply the paradigm to nature, but nature is itself constituted in our observations by the paradigm. So any sort of correspondence interpretation of science falters. Rather, what we must have is what we could call a coherence interpretation of a paradigm or of science. Is an anomaly coherent with, or an observation coherent with what we should expect from the paradigm itself? And that is why, if we think of that, that our truth or our grounds for belief in paradigms will be based on coherence in science. A scientific account of science would itself have to be paradigmatic, which is why we can say that Kuhn's paradigm is in fact a paradigm of science. And this is a very curious and funny thing, but you'll find in the 20th century lots of these apparently self-referential theories anytime you turn to coherence. Right? A paradigm of science, whose paradigm of the paradigm is the visual gestalt. The early Wittgenstein had a picture of language. Right? Language pictures the world. Wittgenstein later figured out that, in fact, that's a picture of language. Right? We have a picture. And I think the breakdown of correspondence theories have led to these self-referential coherence theories. But more importantly, they've also loosened up something I would call, the great French philosopher Jacques Derrida calls free play. The possibility that science may not be the litmus test of all human intellectual activity, that we may not want consensus on such issues, that openness, free play, flexibility, the creating of new conceptual schemes might in fact be the value of a large amount of human intellectual endeavor.